Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Functions, Basics. Concept number 6, Domain of a function. The odds of someone doing exactly what you tell them to do is slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. If I could stick every math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose by ordering and purchasing the complete cram session. You have lots of friends, classmates, colleagues, and or pairs who are taking Algebra 2 alongside you. Tell them to inbox me at memedicine@gmail.com so that they too can order the complete cram session. Let's delve into the concept. Function basics, domain. What is the domain of a function? Definitely press pause if you need to, and I'll give you a moment to think. All right, so the domain of a function is the set of all passable values for the independent variable, usually called x, or the input variables found along the horizontal axis of a coordinate plane. All right, and as an example, let's take a look at the domain of the trigonometric function, the tangent of x, for a holistic review. Okay, so the domain of the function tan x is going to be all real numbers except odd multiples of pi over 2. And you can clearly see that at every odd multiple of pi over 2, there's an interruption in the domain, okay? But other than that, it traverses from 0 on out to infinity, all the way out to negative infinity, with interruptions only at odd multiples of pi over 2. And we'll see why this is in a little bit, okay? Just in case you forgot what a real number is, a real number is a value that represents a quantity along the number line or x-axis, although here this axis is in radians. Pretend it's just in regular numerals, okay? And the real numbers include all rational numbers. And rational numbers can be written as a fraction, let's say a over b, where a and b are integers, but the denominator b is not equivalent to 0, but it can be equivalent to 1. And when written as decimals, rational numbers either terminate or repeat. Okay, so some examples of rational numbers are the integers -5 and 4 over 3. Okay, as a decimal, I don't know, this would be 1.33. Okay, all right, and previously I just said integers. Integers are basically counting numbers that you find on the number line, such as -2, 0, and 1. And remember that implicit underneath every single number, there's always a fraction bars 1. That's why it's still written in the form a over b. Okay, same thing here, even under 0 and under 1 as well. Okay, so just think of each number in that way. All right, let's move on. And the real numbers also include all irrational numbers. Irrational numbers cannot be written in the form a over b, where a and b are integers and b is not equivalent to 0. And with irrational numbers, when they're written as decimals, they don't terminate or repeat, okay? So an example of an irrational number is the square root of 2. When you convert this into a decimal, or after evaluating the square root, it's going to be 1.41421,356, ... The decimal goes on forever without terminating or ever repeating, at least not to human knowledge, okay? All right, and so yeah, this takes care of real numbers. Now we're going to see why odd multiples of pi over 2 or 90 degrees. Remember, pi over 2 is the radical value, the radian value, not radical, of 90 degrees, and the conversion factor between radians and degrees for an angle is going to be pi radians over 180 degrees or 180 degrees over pi radians, depending on which value system you're trying to use, okay? All right, so in a trigonometry basics cram session, we established that the unit circle has a radius measurement of 1 in any direction, okay? And this greatly simplifies finding all trigonometric values, including the tangent of any angle x, all right? Okay, I'm going to show you why that is. Let's say that we have some point P located right here. And this point is the intersection of the unit circle and the terminal side segment of this acute angle theta. Okay? And we're going to say that P cuts off this segment between the point 0, 0, because the center of a unit circle is at the origin 0, 0, and the point P. So we can then resolve this terminal side segment of this angle theta into its x and y values, okay? So x being located right here, corresponding to this x, and y being located here. And what we can also do is resolve the terminal side segment into its components. So the initial side ray, or the x segment on the horizontal, and then the vertical side traveling upwards, corresponding to the magnitude of y. So this side has a magnitude of x, and this side has a magnitude of y, okay? And what we also have here is what seems like a right triangle, because the newly established vertical segment is perpendicular to the x-axis, or perpendicular to the horizontal segment or initial side ray, okay? Alrighty then. So this means that the coordinates of the points where the coordinates of these points also can correspond to the trigonometric values of this angle theta. We know that just in general, for this angle theta, that the cosine of theta is going to be equivalent to the adjacent side divided by the hypotenuse. But here our hypotenuse length is actually the radius measurement of 1. So this greatly simplifies finding the cosine value of this angle theta, which is just going to be cosine, okay? Because the cosine of the angle theta divided by 1 is just cosine. We don't need to be redundant and write this. And the cosine value also responds to the x coordinate, okay? Which is the x value for the point P on the terminal side segment. Now we could also say the same thing for finding the sine of this angle theta. Sine in normal trigonometry is just going to be the opposite leg of the triangle divided by the hypotenuse. Well, we know that the hypotenuse length is 1, so the sine of theta is just equal to the magnitude of y, or y is equal to the sine of theta, okay? So now we have a way of interchanging between trigonometric values and x and y coordinates for specific angle measurements based on their terminal side segments. Okay? I hope I didn't confuse you too much. I may be confusing myself, and I know this is getting a little lengthy, but just continue to bear with me because I think you're doing a great job, okay? And this means, again, that the coordinates of the points where the unit circle intersects the x or the y-axis can be conveniently used to find trigonometric values because they're quadrantal angles. Now, we said that earlier pi over 2 is 90 degrees. Well, guess what? 90 degrees is located right here. And its terminal side segment basically has an x value of 0. Therefore, the cosine of 90 degrees is 0. And the y value has a corresponding y location of 1. Okay. Therefore, the sine of 90 degrees is 1. And we know that the tangent of 90 degrees is going to be the value of its sine divided by the value of its cosine. Therefore, 1 over 0 is undefined. Hence, we get these vertical asymptotes, first at pi over 2 and at every interval where we have a quadrantal angle that is basically an odd multiple of pi over 2. Notice here that for the quadrantal angle 180 degrees, the cosine value or the x value is going to be 1, while the sine value or the magnitude of the y is going to be 0. Therefore, 0 over 1, or the sine divided by the cosine, is just basically 0. So that's why at multiples of pi, you get 0, 0. And remember, pi radians is 180 degrees. I don't know, I probably confused you a little bit, but just, purchase the trigonometry series that explains this as well. And this was way off topic because we just really wanted to know what the domain of a function is. But I'm trying to integrate a little bit of Algebra 2 trig with the basic concept of functions as well, okay? It won't hurt you to know. Don't get all wound up if you don't understand what's going on. Thanks for tuning in.